Time to get off LinkedIn. And hold on, let's pause this here. Let's move some things around. Okay, so we left off with our tests failing, and unfortunately, because our tests are failing, we have to write more tests. So right now, the only thing we really wanted to test was this main, where are you? This function right here, right? So we want to be able to get this OpenGL PAINT5D get function into our shader code. So we wrote a test for it, and that test is failing. And because of that, we have to write more tests for the other sub-functions that that function uses, right? If we could have got the test to all pass for this top-level function, we'd be done writing tests, because we wouldn't have to write the individual tests for all of the different sub-functions, right? That would be unnecessary. It's like if you test a chain and the chain holds the payload, you don't need to test the individual links of that chain. Same thing with this. If the overall main function is tested to work properly, we don't have to test the individual sub-functions. But unfortunately, that's not the case, and we do have to test those individual sub-functions. So we're going to have to start subdividing up our unit test for P5D OGL. So right here, P5D OpenGL, which is a it's conceptually it is still part of PAINT5D, but we've just put so much stuff into PAINT5D that I thought, you know, let's kind of put this in its own file, right? I don't believe in getting too coarse with how we write our code. However, I'd say that, seeing that this is line 7,000 and change, I'd say we've put enough stuff in this file, and it would be reasonable to move things into another file. So, everything in this file, except for this little polyfill here, is something that I want to be able to just cut and paste into the GLSL source code. So everything you see with this little X at the end of it is I want to take this whole block and just throw it into my shader code once I've confirmed that it works properly. So we know that this is not quite working, so now we have to test the other sub-functions. And since we already have code that confirms that the individual functions written on the CPU side work. Oh, okay. Oh, thank you. So I'm on the wrong screen. Yeah, I am on the wrong screen. So this is why I need more people to view my stuff. That way I can see that I'm on the wrong screen. So let's shift some things around here and then think about what we have to say again, because we're on the wrong screen. Alright, so over here, this file is a file just for the code that I want to paste into my GLSL shader, and they're all rewrites of CPU side code. So instead of using the namespace AAC 2020, the namespace is OpenGL. Right? So this part of the function name mirrors exactly, this part of the function name in the yellow mirrors exactly function names in the file to my right, but we have rewritten them in a way that will make them easy to cut and paste into our GLSL shader code. And because our GLSL shader code, and because our CPU side functions have already been tested, we don't have to think too hard about how to test the individual functions here. We can just cross-check the GLSL version of the function against the CPU side version of the function and see if they get the exact same results for the exact same inputs, and if that happens, then we're good. So let's start testing the individual sub-functions here. So let's just kind of go up in order, right? So PAINT5D get is right here, right? And then if we scroll up, we see the next thing is this thing here. So what we're gonna do is we're gonna just say, you know, extern void AAC 2020 P5D OGL unit test code, and it's gonna be PAINT5D this whatever. Okay. So we're running out of room. So I'm just gonna put a V for void. And then over here I'm gonna say define V, and V is gonna be void. And then undef V over here. Okay. So this is getting kind of out of hand in terms of how long this function name is. So test. Right, so if we want to know what we're testing, we might as well kind of put that in parentheses so that we know what we're testing, right? This is what we're testing. Here's the function we're going to use, and we're going to just kind of, let's just kind of use overwhelming force here and say, you know, we really don't want to have to test, like, every single one of these subfunctions, but the thing is that it's going to be faster, I think, to just test every single subfunction rather than to kind of try to guess about what we did wrong, right? I'm sure that we did something wrong that was completely stupid, completely simple, but looking for that one simple, stupid mistake, and all of this code is like looking for a needle in a haystack, so we're not going to do that. So we're going to keep on creating function names here. So AAC 2020 PAINT5D, right? So this is the first part of the namespace. This is, you know, yeah, this is a lot of stuff. And we don't want to call this with any parameters. How do we do it over here? We just forgot the parameters. Let's keep on scrolling up. Now, it might be nice to... we don't really have room to write it like that, do we? Well, if we did that, we could get it to line up. So I'm just thinking it'd be nice to be able to see what we're testing really quick, to see this all kind of line up here, so we can see the pattern of what's going on here. Then over here, this is, you know, what are we testing here, right? We might as well make a note of what we're testing here. Let's keep on scrolling up. So we have this guy as well, so we're going to keep on cutting and pasting here. And what we're testing here is this thing. So we're going to just go like this, go BAM! That's what we're testing here. And scroll up to the next function, this bit packing. We forgot the T here. And then we're outside of here. This texel fetch is, you know, if we get it wrong, we get it wrong. We're hoping that the texel fetch is not the wrong thing, right? We already fixed this code because we found a bug in it. And so we're pretty sure the texel fetch is wrong, but we may have to come back to it if all of these different tests that we're stubbing in right now are failing us. So let's look at this last thing here. So that's the last function here, a function that we actually care about, and this is what it's called. So we're gonna say test and put this here and line that up kind of like here, and I see a problem, which is why is this lowercase? That shouldn't be lowercase. That's not how he named it, right? We said the get. Despite what it might look like, our function names are actually camel case. And so those should be capital G's. So let's look for where we're calling all of these. That's all. Okay, cool. So yeah, let's just open up our clipboard stack and start pasting this in here. And did we already kind of make a section to... Yeah, unit test section for PAINT5D code. Okay, so what we're going to do is we're going to start the clipboard stack, go cs start, and we're going to grab all of the functions that we need to write. So we're going to copy, 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 copy. Okay. Then we'll do a cs dump. And also, it's important to note that the order here, the order of these functions is from lower level to higher level, or most dependent on to least dependent on. Functions are tested in order lowest level to highest level, aka most depended on to least depended on. Right? So we gotta test this in the correct order so that we can find the root cause of any mistakes, right? So, for example, if you're trying to test a brick, and the brick fails, you might want to you need to go back a few steps to see what the root cause is. You want to go to the lowest level. Is the cement mixture that is used to make the brick, is that failing? Are the furnaces failing? Are they not like drying the brick properly, or etc. Right? You want to look at the low level components first, right? Because if any of these low level things fail, well, they are all, anything back here is used up here, right? So we want to test the things that are dependent on the most before we test this highest level function. Because once the test fails, we want the failure of the test to reflect the root cause of the error, not to be a symptom of some other piece of code that is dependent on failing. So let's make a note of that. So it's video 87, and the time is 23 minutes and 32 seconds. And so yeah, once again, stating for the camera, you want to test the small grain functions, the functions that are depended on the most, before you test the functions that have the least amount of dependencies. You want to test from low level to high level, so that when you do get a test crashing, it's actually or a test failing, it is the root cause, not some type of failure that has bubbled up into a higher level function. Okay, so now we need to let's highlight these, make sure that everything is accounted for. So if I highlight all these functions, we should have, yeah, everything's colored here. Cool. So let's just make a little template here. So void xxxx void and then something like this, and then something like this, and then maybe a dash line I1 x64. So just make a little template like this, and then we're going to make a cut and paste this code a few times. Alright, so we're going to take this, we're going to look for all these x's, and we're going to replace it with these new function names that we need. Alright, so take this. Okay, cool. So now we have the functions we need are kind of like stubbed into place. Now we gotta like change the formatting a little bit and remove some of the extra spaces. And okay. So we do have enough room where we could just be like, you know, we could just kind of throw this here like that, and take up a little less room. So, you know what? If we do have all that room, I think that's how we're going to do it. Yeah. Now, I could regret this decision later. But we have enough room, and we can take up less space doing it this way. So let's just do that. Okay. So the first thing we want to do is say, you know, I'm pretty sure that the functions will work the way they are. I do like 1 point of return at the end. I like explicit returns. So yeah, if we stub that in, if we stub this in, I think that we can get the code executing again. The test will fail still, but I just want to make sure that all the stuff I just wrote is, you know, proper. And yeah, so we still failed that first PAINT5D test. We see that the pixel X, pixel Y, it failed when pixel X was 64. So that's very interesting that we're failing on this power of 2, which makes me think it's a problem with the tile exponent. But we're going to forget about trying to guess about what the problem is and just kind of fill in these functions. Oh, actually, we have these kind of in the wrong order, don't we? So if I highlight this, where are you? Are you up here? Yeah, you're up here. How did I make that mistake? That sucks. So we're better off. Honestly, we're better off. It sucks that we made that mistake, but we're better off just doing it again. So CS start. And we're just going to grab all these things. How did I do that? Did I just copy them backwards? Yeah, so we want them in the order of dependency, right? I mean, they're all 4 declarations, so technically it does not matter. But we want to be able to make sense of how we're writing this code. Just keeping a consistent ordering here, right? Having them appear in the same order as they appear here makes a lot of sense to me. I think it's going to help us avoid a lot of problems. So void and xxx void and then something something, right? So we're going to take this and try one more time. Hey, how's it going? Okay. Yeah, today so today I'm writing tests for code that I'm going to paste into my GLSL source. So GLSL source code and C code are very similar, and they're similar enough that if I'm careful about how I write my C code, it will also be valid GLSL code. And so I'm rewriting a lot of different functions, but writing them in a specific way so I can cut and paste them into GLSL code, which is kind of hackish, but it's the best solution I can find. I want a lot of reassurance that my code works before I try to get it into GLSL, just because GLSL is very hard to debug. It's very hard to debug shader code. So if we can get a lot of that debugging and double checking done on the CPU side, we're going to be in a good place. So anyways, let's take... Here's my replace keys. We're going to take this little template here. We're going to paste it here. We're going to look for anything that says XXX, right? So this is my find and replace template. Right, so just something I use to auto-generate code really quick. When I have like a lot of redundant code, right? This is just redundant. Well, it's not. Well, this part's redundant. The signatures are redundant, but whatever goes inside here is obviously not going to be redundant. So I'm just going to put my 1 point of return. I don't know where I want it. Just put this here for now, so I don't forget about it. Okay. We're just going to give that a run, make sure that is working. And, looks like it's working to me. No syntax errors. Okay, yeah. So, this is the first thing we want to test. And if we go into the code, so we're going to go all the way up to the top of this code that we want to paste into our GLSL shader. And it's this bitpack get function. And it takes a global X, global Y coordinate, and an offset index, and it's going to get a bit pattern from that. Hold on here. Where's this U32 variable coming from? Oh, a texel fetch. Okay, so it does its like texel fetch kind of thing. Okay, so that's fine. Do we have a bitpack put? So let's just look around and see kind of what we have here. I don't think we have a bitpack put function, but I don't know. Let's see if we have one, because I don't think we wrote one, because we were like, oh, we're not going to write one because then we would have more functions to test, so we didn't do it. Or I guess we did, huh? Okay, cool. So we have a bitpack put, and that's actually kind of helpful to us. Because we can use this function to help us test what we've been writing, right? So we're going to get into like a little loop here, and we are already assuming by the time we get to this function has already been tested, and we're going to use this function to cross-check this function. So we're going to use both the put version of this function and the get version of this function that have the AAC 2020 namespace to test this function that has the OpenGL namespace. We're going to cross-check, right? So let me check my Twitch whispers here for a second. I will check those later, because I see you messaged me, but okay, so how are we going to do this? So CPU pixels, global index, global, yeah, so we could once again kind of iterate through every single pixel on the bitmap. It seems that, you know, spot checking is error prone, where we might miss something, so I think that the XY kind of loop here that we've been doing is kind of a good thing. So let's kind of take all of this. Like, I think I can take a lot of this code and reuse it over here. We don't really want this commentary, and we don't really want this commentary as well. We do want to skip over things that are invalid, and for px and py, for all these values, I think it would be easiest to Tile value, huh? So tile value is here? Okay. So I don't know what kind of variables everything needs. We're just going to make int32 versions of all of these, and then do the proper downcasting depending on what we need here. So so we're just gonna do like int32 tile value and int32s of these. So 1, 2, 3, 4. Px and py will also make those int32s. And then int32py. Okay, now this here, oh, I see. So this os here, yeah, we're going to change up some of this. And for the time being, we're just going to cast it when we do the put, I believe. However, you know what? The put function probably, when we get the values back, we probably need a very specific, let's put a breakpoint here. We probably need a very specific, so they're UO8s, yeah, so everything's 8 bits, that actually makes sense. And the getter, okay, yeah. So this is 8-bit, 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 8-bit. For the put, it doesn't really affect us too much, because we can just do this, we can just cast, and we're good to go. However, with the getter, right, we put the value, and then we get the value. That's going to be a little bit harder. So this tile value here needs to be 8-bit for this. So because we're going to pass this by reference, we need it actually to be the right bit width. So I'm going to say, you know, just gonna call that UO8 tile value like that, and we'll just assume if it doesn't have a specifier, we'll just call it, say that it's, you know, it's int32, and the tile value here plus plus. If that's how we want to do it, we can do that. So kind of generate a tile value here, and generate tile value. So there's two things we're doing in here. We're generating a tile value. Right, so we're generating a tile value based on, well, nothing really, actually, just kind of cycling between 0, 1, 2, and 3. And we're going to skip over the configuration pixels. So now why is this like this? Why do we care about that? Oh, because it's used here. Okay. I feel like that's a little bit... I don't know. Well, let's just keep it like that. Let's not worry that there's this other thing here that doesn't really belong in this category, or we could. I think we have enough room where we can indent this properly, and then this is, I'm just gonna call it the setup, because there's actually 3 things being done in here, and so this description is also wrong. And I'm kind of sick of writing the description, so let's just call it the setup here. And for the bitpack get, we're going to use this U08 value up here. So I'm going to take this, and it needs to be a reference this time. And so I know we already wrote the code to test these 2 functions. However, we might as well, since it doesn't take too much extra work, make sure that this guy works first. That if you put something, you get back the same thing, before we try to cross-check. So, because if this does not end up being this, then it doesn't matter if we were very careful about transcribing to get this code, because we transcribed from erroneous code, so it just doesn't matter anymore, and we have to, we'll be in a very bad place if this part fails. So let's hope not, because we already wrote all the test code for that, and so now we're kind of retesting some stuff. So, if this is not equal to, okay, then we failed everything. Our problem is in the original code. So we do not, hope you never see this error. It means okay, so we're gonna hope that we never see this, because if we see this, it means we transcribed buggy code. And the time is, okay. So yeah, if we see this error here, we are in some serious trouble, because we're just retesting the CPU side of this function by putting a value and getting it back. And if this value fails to match this value, then we're just in trouble, man. Now, the other thing is, this is an 8-bit and this is a 32-bit, right? So we do have to make sure that we do like a U08 cast, or some type of cast of both of these. I'm thinking, let's cast them both to something that they... Oh, hold on here. When I did my comparison in the other function, did I cast a 8-bit integer? Because I was like, hey, let's if we try to cast to 8 bits here, hold on here. Okay, 8 bits is, oh, right here. Yeah, can you not hear me, or, yeah, is my reception bad? Let's see here. Yeah, I can try to clarify, though I am really deep in a lot of code, so it's like, it's hard to say exactly. Okay, yeah, so, here, let me, I can backtrack I'll backtrack for you. Okay, yeah, I'm going to backtrack for you really quick and explain what I'm doing here. Let me make sure this is... we'll get to this. We'll get to this. To do... Okay, so let's go to the diagrams. Let's go to the diagrams. I think having a picture is going to help. Okay. Okay, so I am trying to make a... do we have a demo of this? So I don't have a demo of this. Let me think here. How am I going to explain this? Let's open up Paint. So the first thing we need to do is kind of explain, well, what am I trying to make here? And I'm trying to make an editor where... this is a lot of backtracking, but we're going to backtrack here. So I'm trying to make an editor where, let's say we have a canvas. Hold on. And... actually, no, let's do this. Okay. So we're going to have a canvas where we're doing like MS Paint kind of graphics, except the catch is that there's different, you could say different pixel sizes. So there's going to be, instead of just having the pixel always be, you know, this size here, down here, we're going to have pixels that are different powers of 2 of each other, and they're going to overlay over each other. So when you have a brush and you're trying to select a tile size or a pixel size, you can select between these different powers of 2 to paint with. So 1, 2, 3, 4. So I want to be able to say if the tile exponent is 0, then it's the smallest tile. If the tile exponent is 1, that is 2 to the power of 1, so it's a 2 by 2. And then, is that right? Hold on. I always get my exponents mixed up. 2 to the power of exponent? Oh, no, it's to the power of the exponent, I believe. So, this is 1 by 1 is 2 to the power of 0. Yeah, 2 to the power of 0, right? So this is the smallest tile is tile size 0. This tile size is 2 to the power of 1. This 4 by 4, 2 to the power of 2. The 8 by 8 is 2 to the power of 3, etc., 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 right? So we want this idea where we have this different brush, where we have these different tile sizes where we can paint with them. Okay, so unfortunately I don't have a tech demo yet because I'm trying to build up to that, but now we have to think about, well, how are we going to store that data? How are we going to store, because we have these overlaid tile sizes that nest directly into each other, we can store the data as a quad tree-like structure. But because we want to store all of the data on the GPU, we don't want to store like some type of linked list style structure. We don't want to structure a heap-like structure. We want a densely packed data structure. So to get that nested structure with those different tile sizes, we can pack all the data into pixels into a 512 by 512 bitmap, and we can partition out these pixels to store different tile sizes. So let's just look at this thing here. Let's not look at any of these quadrants here. Let's just look at this. So this is a partition of a 256 by 256 block of pixels. And it corresponds down to what the artist is going to see. So this is like what the artist is going to see in the editor. And the artist is going to have tile exponents 0 to 7, and the smallest tile size 0, has the most number of pixels that need to store it, because the smaller the pixels are, or the smaller the tiles are, the more of them you're going to need to cover the entire canvas, right? So you have 128 of the smallest tiles. If you use tiles that are half the size of the 128s, then you need, if you use tiles that are twice the size of these, you'll need half as many. So the next cluster of tiles are from this partition of pixels. And then if you want tiles that are half the size, if you want tiles that are twice the size of this, you need half as much. So you go down to this partition. So it's kind of inverted here, where this biggest chunk stores the smallest tiles, right? And the smallest chunk of data stores the largest tiles, right? Because eventually, once you get down here, you only have 1 pixel. And it's 1 pixel that stores 1 gigantic tile that covers the entire screen. Now you'll notice that the partitioning here is a little bit weird, where I said that, but why are there these 3 chunks here, right? There's 3 chunks, and the reason for that is because we're going to use 3 different painting layers for the editor, just because the data kind of just packs very nicely that way. So this will be the smallest tile size, layer number 0, the smallest tile size, layer number 1, and the smallest tile size, layer number 2. And this is all the data for rendering this section here of the graphic. And this section of the graphic is going to be like this tile design, or this meta tile design that my artist is going to create for a auto tiling engine. So this is the graphical editor for that. So you could think of what I'm designing as just take MS Paint and then just add different layers to it and different tile sizes. Or you could think of them as pixel sizes. I'll call them tile sizes, so we don't confuse the tiles, what you see in the editor, versus the actual pixels storing those tiles, which is here stored in the data. Right now, so you see this is 128, so there's 128 of them, 128 by 128, and this section here is 128 by 128 smallest tiles in size. Like, the size of this is relative, because the artist can zoom in and out on this. So this is 128 by 128 smallest tiles in size, because the data right here is 128 by 128 pixels, and those individual pixels are storing the individual tile values. So it gets even more complicated than that, because there are 32 bits per pixel, right? And that's many more colors than I actually need for this editor. We really want to leverage how we're using our data. So what we've done is we've decided that each pixel is actually going to encode more than 1 tile value. So when we look into a single pixel, we have 32 bits in a pixel, and every 2 bits is going to actually store 1 tile value. So the tile values that we're storing are actually only going to be 2 bits, and we can store 0 to 15 here if we use only 2 bits of a 32-bit integer. What that means is that in addition to having these layers, we can also break apart the bits to store 16 different unique copies of this data, or 16 different sets of this data. So, to explain this again, let's say that what I explained with all of this, say that we only used 2 bits of every single pixel to encode all of this data, because that's what we're doing, right? We only use 2 bits, right? So, that means that we can have 16 different save files or like sets of this kind of data, all packed into the pixels. That's a bad explanation. But right, we're only using these 2 bits here of the pixel, and so what are we going to use? What are we going to use for all these other bits? Well, we'll just use these for different tile designs, right? So this data here is being used to render a tile design, an auto tile set that's composed of 1, 2, 3, 4 subtiles. It's the artist's job to make this design the top left corner, this the top right corner, this the bottom left corner, and this the bottom right corner. So that's the artist's job, to design the graphics in such a way. And once they have designed this graphic will have only used 2 bits of every single pixel in the GPU data that encodes it. Okay, so we only have 2 bits to create this entire auto tile set. And since we've only used 2 of those bits, that means that the GPU data can actually encode 16 unique auto tile sets, because we've only used 2 bits of those 32 bits to create one of these graphics. So that is kind of, it's kind of hard to wrap your mind around, especially because I don't have a good visual for you right now. So this tile exponent here is the tile size, right? So we're going to, right, like I said, the tile size is going to be in terms of powers of 2. So if the tile size is 0, it's a 1 by 1. It's the smallest tile, right? So it's since it's the smallest tile, it takes up 128 by 128 tiles. The next tile exponent size up is twice as big, so there's only 64 of them, right? There's half as many, 64 by 64 of them, because it's overlaid directly over the 128 by 128. The next tile exponent up from that is twice the size of the previous, so there's only 32 by 32 of them. The next tile exponent up, right, is once again half the size of the previous, so there's only 16 by 16 of them, right? And we keep on going up until we get the largest tile exponent, which is tile size 7, which is this gigantic tile, right? And it's so big that there is only one of them in the editor, because it just fills the entire canvas. So the tile size exponent 7 would be stored here, somewhere in the data, in this bottom corner here. And it would be so big that it will fill this entire area right here. Okay? So these data structures here are identical, right? So how I partition this, how I partition this, how I partition this, and how I partition this are all completely identical, right? Because they're all used to create a graphic here, a graphic here, a graphic here, and a graphic here. So we have to figure out a lot of the math of how are we going to abstract the data to where we say I have a certain tile layer I want to draw on, and a certain local coordinate, and a certain tile exponent, and I have all these different parameters. How do I map that to a very specific pixel? And that's the logic we're doing right now. We're trying to have an interface where we can say, here's the layer and the tile size I want. Give me the correct pixel that is encoding that data. So now, we've already written that code, but we didn't write it in a way that could be used in GLSL code. So we have now rewritten a lot of these functions for our GLSL code, and we've namespaced these functions OpenGL. So these OpenGL namespaced functions have an equivalent function of the same name in the file to my right. And those functions have already been tested in the file to the right, but the functions on the left are rewrites of the functions on the right, and we need to test them. And because these functions are rewrites, all these functions are rewrites of the functions over here in the right. So in order to test them, all we have to do is run the original functions and then cross-check them against the rewrites. And you're going to wonder, well, why am I rewriting this code here? And the reason why I'm rewriting it is we did some things that we cannot do in OpenGL or in GLSL in the original functions we wrote. For example, if you see this function here, it is taking a reference here, or it's taking a pointer to a value. And we cannot do that in GLSL code. Everything must be passed by value in GLSL code. So we have to write a different version of this function that takes these three as input parameters, and instead of outputting it as an output parameter here, this needs to be a return value of this function. So if we look at this function here and find it in the left screen, we can see that we have rewritten it to be a little bit different here, right? So this U32 that it's returning is this tile value, and this glow and OSDEX are this and this, and then the thing that says CPU pixels, this is a pointer to a bitmap that we're going to be extracting the data from. But remember, we can't use pointers in our GLSL code, so this version of the function is hard-coded to use a very specific texture in the GLSL code, right? So this rewrite, right, is not a one-to-one remap of this. Well, it kind of is, kind of isn't, right? But it has to be rewritten for the purposes of being used in the shader code. And then to test it, we can do the CPU side function of the put, the CPU side function of the get. Then we can compare what we got just to make sure that we can make sure that this value and this value match each other, right? That whatever we bitpack put, we also were able to get, right? Make sure that the original function still works. And then once we know that the original function works, we'll take this bitpack get function and we'll use the same inputs and make sure that for the same inputs, the output will match the output of this function here. So we're going to cross-check it. Okay, and then what we're going to do is after we get this working, we're going to take all of this code here on this side of the monitor, and we're going to paste it into our shader code. So this is our GLSL shader code, and it's kind of annoying to write because it needs to be inside of a string, right? So what we're going to do is we're going to do something like this. We're going to take our, once we get this code working, we're going to take it, we're going to copy it, and we're going to like paste it into some shader code. And the way I've written it so that I can just strip it down like this. And so this says do not paste in GLSL code. So we can remove this. And then we can just put some, we can turn it into a string, right? This is very hackish, but whatever works. Whatever gets something working, right? So we can just wrap all of this code in a big string to put it into a shader string for a GLSL shader, right? And then have this in our GLSL code, right? So how is this going to work in GLSL code? Because C code and GLSL code are not the same code. They're very similar, but not quite the same. Well, you'll see here, I've been very careful to make a kind of like a little translation layer. So both GLSL and C code both have defines, and because they both have defines, we can make a macro in our GLSL code that says if macro this is GLSL, then we're going to say that U32 maps to uint, I32 maps to int, IV2 maps to IVEC2, TF maps to Texel fetch, P5D matches to PAINT5D, and then when it's running on the CPU side, where we're trying to test it and make sure that it works properly, these same tokens map to their C equivalents. So the uint32, int32, there's no vec2 type in C code, so we made a little struct for it. And for our Texel fetch, we made a polyfill of Texel fetch. So this will mimic what Texel fetch does in the OpenGL code, right? So we have a little adapter here to make it so that this code down here that we have written will run both in C code and in OpenGL code. Now, it is kind of hacky that we're going to have to test it, and then after it's tested, we're going to have to cut and paste it. And so that's also why I kind of put these comment characters around it. That's just for me to say, don't change this. It's kind of like sealed, and it's a really, really hacky way to do it. However, one of my goals is to make sure that the final executable is just an exe, that there's no installer, that there's no other supplementary files that need to be in the same folder with it. And because of that, I can't just, like, it'd be very nice if I could just have this code, right? Another solution, which is less hacky, but goes against the way I want to organize this code, is we could take this code, like this, exactly like this, we could put it into its own file, and for the C code, we could include it, and then be able to test it, and then for the GLSL code, we could, when we're setting up our shader, we could instruct OpenGL to read this from disk and load it into our shader code. We could do that. And that would be a more robust solution, because we would take the exact file verbatim and automate the process of testing it in the C side as C code, and then also pasting it as is into the shader code, automated. And if the shader doesn't crash, and the CPU side code says that the tests pass, then we have a high level of confidence that the code is correct in our GLSL, right? But if we want to automate it like that, we would have to distribute our executable with this file, right? We would not be able to embed this file into the executable. And the goal is to embed all of our code into the executable, and so that we don't need to we don't need an installer for our program, right? If people want to share the program, they can just share the exe file, and they don't need to take a folder with the exe in it. They can just share the exe. They don't have to have any supplementary files to go along with it. Because I'm doing it that way, the only solution that does not invoke any undefined behavior for my compiler is to, write some tests for this code and then copy paste this code into some shader code and do that manually. Now, I could write some type of bash script to help me out with that, to make a little build system, but if I do that, then we've made the system a little bit more complicated than I want it. And I don't really want it like that, because then it makes it a lot harder for people who are unfamiliar with C code to run my project, because now I got this like crazy build script. So I don't want any crazy build technology going on. So unfortunately, we're going with a very hacky kind of solution here. So what else here? Yeah, I mean, so in general, it is very hard to, it can be since I'm in very deep with what I'm trying to do, it can be very hard to understand what I'm doing, and that's not anyone's fault. That's just the nature of, I've been working on this idea for a few months now, and I've had the idea in my head for like 8 years. And so I have like a lot of a lot of mental models that I may have a hard time kind of expressing. And so to get the big picture will be kind of hard, and I will try eventually to make it a little bit more obvious what's going on. But yeah, it's going to be kind of hard for me to explain. But I think that it is a good, like, if you ask me to explain, I'll try to explain. But yeah, there's only so much I can do, but I think that I will keep on trying to explain, right? Because I think that it is good for me to, if I can't explain it, then I don't know it well enough for myself, right? So anyways, let me close this. And it's been an hour, so my girlfriend wanted me to do some laundry and whatnot. So I think I need to get to doing some laundry and be back in a little bit. But here, let me check my messages from you for a second. Okay. 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 Yeah, so I think what I'll do is I will try in the future to... I want this to be as well documented as possible, because I want other people to eventually be able to use this engine. So if people don't know what's going on, that's bad for me, right? Because people need to understand how this works, otherwise no one's going to be able to use it. So I'll try to create like little tutorials to explain what's going on, maybe. But yeah, there's only so much I can do here. So I have to do like some laundry and whatnot. So I'm going to let's see, it's been an hour. I'm actually gonna try like I'm gonna try 40 push-ups, and I think I'm gonna end the stream right now. Just because I said I was going to do laundry. So, let's see. Push-ups. Today was 40. These totals are not correct. I need to reset these. So we were basically streaming for an hour. But yeah, I need to do some stuff. And I want my stream to be a pretty accurate idea of how much work I'm getting done. So, because I want this stream to be an accurate representation of how much work I'm doing, I need to... I need to not go on as many long breaks and just stop the stream and start again. So I'm going to mark that up to 80 because I'm going to do 40 more push-ups when I'm off stream. And I'm going to change this thing as well. But yeah, I'm going to get out of here. And hopefully I'll have some better explanations, but it'll be a while, right? Until I get graphics up and running, my code might be hard to explain. I hope to have a better... Yeah. So yeah, I hope to have some better explanations for you in the future. However, I need to get out of here. So I'll be back in maybe a half hour. Yeah, it's, until I get, I'm very close, I'd say maybe in a month, I say close and I say a month, but maybe in a month I'll have the first version of the editor up and running. Once I have that first version of the editor up and running, I will message everyone who's following me to say, hey, we're going to do a tech demo. And then hopefully that'll make the code that I've been writing a little bit easier to understand, because there is a lot of mental models going on here that are just they're just crazy. And I understand if you have some trouble understanding what's going on here. I totally get it. Like, you know, when I come back to old code of mine, I barely understand what's going on. And so, and I'm the one who wrote it, right? So, I'll try my best to make it more understandable as we go, but it will probably take a while. It'll probably take a while. But I'll try to find a way to make some type of short videos to explain how all of this works. Okay, so I'm going to end the stream, and I will be back in maybe a half hour, so I will see you around.